Welcome everybody to the Fellows Seminar. I'm Sue West, and I'm very pleased to bring Brad Malin in from Vanderbilt University to speak about scalable methods for privacy-preserving record linkage. Brad Malin is Vice Chair and Associate Professor of Biomedical Informatics, as it says here, in the School of Medicine at Vanderbilt University. His research is in big data health analytics and infrastructure necessary to support such investigations, including high-performance computing environments and privacy-preserving technologies. He's the founder and current director of the Vanderbilt Health Data Science Center, and his research has been cited by the U.S. Federal Trade Commission and featured in popular media outlets, including Nature News, Scientific American, and Wired Magazine. He's received several awards of distinction from the American and International Medical Informatics Associations and was honored as a recipient of the Presidential Early Career Award for Scientists and Engineers. Dr. Malin completed his education at Carnegie Mellon University in Pittsburgh, where he received a bachelor's in biological sciences, a master's in machine learning, a master's in public policy and management, and a doctorate in computer science. I'm really looking forward to your talk today, and thanks for joining us.
People. All right, so before I get in, this is work that has spanned a decent amount of time, and the funding for it has come from a lot of various environments. So the NIH has been interested in this notion of just privacy and integration of records. We've had some funding from the National Science Foundation, and most recently the Patient-Centered Outcomes Research Institute. And the relationships that we've ended up building along the way to get the research done that you're about to see has ended up taking us into a lot of different academic institutions, as well as we've been doing some work with Google, who happen to be some of our former students who are now taking this over there. Okay, so let's begin with an example. I don't know everybody's background. But how many of you are familiar with the concept of the mini Sentinel program that the FDA has established? Okay, so Sentinel started, about a decade ago. They tried to get this idea up and running, and the whole point was that you're going to do adverse event detection, and so the FDA wanted data to come in from across the country. So you have a situation in which you might be looking at post-market surveillance, right? You want to see what happens once things are out in the wild. It's what you might call like a pragmatic trial at that point. So you might be interested in what happens with people on clopidogrel, or Lunesta, or simvastatin, or Flonase, or pick your favorite drug, right? And they basically want to see what happens over time once that drug is out in the market. So when the FDA started this program, they said, we only want to see de-identified data. And so that made things interesting. And one of the reasons was that the events are not all localized to a single environment. So you've got an individual, they go to a particular hospital, they might have had OxyContin prescribed to them on December 1st. And then in December 7th, about a week later, let's say they end up, for some reason, on warfarin. Maybe they've had some type of a stent put in their heart. And then 3 days later, myocardial infarction, they end up presenting back at a hospital. Okay, so you've got a couple different visits. Now the challenge here is that what we see is that patients are mobile. So they don't necessarily just go to a single hospital, they'll go to a second hospital, they go to a third hospital, and the events that I just described to you all get jumbled around, have the potential to. They don't necessarily, but this can happen. Okay, so this is one of the concerns that we have. Now, initially, when I first started on this research, didn't know how widespread of a problem this was, and then the Regenstrief Institute up in Indiana took a look at what was going on in their own region, and what they found was that in about 1 million patients in central Indiana, about 50% of them were visiting more than one hospital, not just one healthcare institution, but one hospital. This was a huge concern at this point. Now we're like, okay, so this is a really challenging record linkage problem. So what I'm showing you here, this is an example of 5 different hospitals in the Chicago region. I don't want to go through the details of what they all are. I think you get the point in that there are flows of where people are going. So this is like a conditional probability. So like, do you start at institution B in red here, and then go up to institution A. That tends to happen a lot, but it doesn't happen that you go to institution D nearly as much. So there are some places that are sinks, and there are some places where people are being shuttled from. Okay, so this was from a paper that Abel Coe, a collaborator of mine up at Northwestern, published a couple years ago, because these were institutions that were in the Indiana region. And so what you see here were two different types of populations. The ones on the left were MRSA admissions, and the other ones were VRE admissions. So this type of movement is happening. So this was from a more recent work that we've done. Here's an example of surveillance. So this is a particular disease, not worth going through what it is, but this is where the hotspots are within the Chicago region. All right. This is what happens if you look at data in a pre-deduplicated form, and I'll show you what happens in a second. So keep this picture in mind. This is the type of thing that we want to study. And this is how many people we see with various diseases. So let's say this is in Chicago. You see 135,000 people with diabetes, 110,000 with asthma, 6,000 with myocardial infarction over the course of a year. So when you are tracking these people, if you do it in a health information exchange, right, like what they have in certain places, these places get to see patient identifiers. So we get to talk about the record linkage problem. And as a result, you can develop extremely sophisticated record linkage methods. And this has been done since the 1930s. People have developed string comparators to see if a name has changed at all. They've developed really beautiful expectation maximization algorithms to weight these comparison rules that you might come up with. So you might weight first names more strongly than gender, let's say. And there are family models. And the reason why family models are important is that what we have seen a lot of is that you have a woman who gives birth. Let's say this is her social security number, and then she gives birth to a child, and the hospital doesn't necessarily have a medical record waiting for this individual, so they create a record. It says, please give us a social security number for this individual, so they end up putting in the social security number of the mother. And then at a later point in time, they don't change it. So you end up with duplication of the social security number. But they know that these individuals are related at this point, so they can resolve that issue. What also tends to happen a lot at Vanderbilt is that patients will call in and tell us, I was seen at clinic A, and then I was seen at clinic B, and I gave them different information because I didn't have all of my insurance information on me at the time. Can you guys link up that information so I have a more complete record? And they go, yeah, we can do that. Okay, so when you get into the privacy side, you don't have any of these things sitting in front of you. So what people tend to do is they'll make transformations of the data. So an example of this is what we call the hash and bash model, where you have a bunch of fields here, names, dates of birth, and a gender, let's say, and then you subject it to some hash function, let's say the SHA hash function. You concatenate all these features, you come out with some representative value, and then you just check to see if these two things are equal. And if they're equal, you have enough resolution here or fidelity, you can claim this is the same individual. So just as an example, it's not worth really reading this. This is just how complex this can end up getting. These are the types of rules that people try and define when they say, what are we going to combine in order to get a representation of an individual? And the reason why you see lots and lots of different representations is you end up with different types of missing information. You also end up with different features that change or are variable at different rates. So this is a strategy that a group up in Chicago has been using that I've been working with, and they've ended up coming up with like 10 different representations. So remember this picture that I showed you, though. This was a particular disease, Chicago region. This was where the hotspots looked like they were before you ran deduplication. This was where the hotspots actually were after you ran deduplication. So there was a significant change to the distribution of where the cases were. And this was how many people I told you had diabetes, asthma, myocardial infarction. We found that there was an overrepresentation by somewhere between 10% to 30% of the individuals in this population. You start running statistical models on this type of data, they will be wrong, right? This was the concern that we had. Okay, so we also, just to make sure that we were correct without telling you exactly what we did, we had a nice gold standard data set. So we had about 11,000 individuals who had been reconciled within a biobank at Northwestern Memorial Hospital. And when we tested to see how well this hash and bash strategy was working within this environment of tracking patients just within Northwestern, extremely specific, pretty good sensitivity, about 96%, so you're getting most of the things back that you want. But again, this is within one hospital system. Okay, so what I just showed you is that you can hash the data, you can check to see if things are the same. And then there's this question of, well, is it actually secure? Who's actually running that process? So if you receive hashes from a lot of different places, do you really trust the person that you're actually giving the data to? This was a huge problem that Northwestern ran into in their clinical data research network for PCORI, because they have 7 different hospitals in the Chicago region, and Northwestern said, hey guys, everybody hash your data and give it to us. And they said, wait, but you guys also have the hashes. So do we really trust you with managing all these hashes? And so then they had to go off and find an independent third party to go off and do the integration. So there's this question about security and how do you remove that third party? So this is where the field of what's become known as secure multi-party computation has come into play. So I'm giving you a couple of examples here again, first names, last names, and cities of residence from 2 different places. And so the notion of a zero-knowledge proof would say that you would be able to test the similarity of these things without disclosing what anything corresponded to in a fully encrypted form. It's magic, okay? And so there's lots of ways of doing what you would call an equijoin, just an exact test, or a set intersection test to see how many records in a database are in common to try and get some statistics on that joint distribution. And so again, you're doing it over records that have been transformed, but notice now these records don't look anything alike. So even the name Smith for now doesn't end up looking the same. And so this prevents a frequency distribution attack. So the name Smith is no longer common anymore. When you go to test this in the encrypted space, you can actually do resolution without revealing what anything corresponds to. Like A matches 1. Okay, so there's magic here, as I was alluding to. So what exactly is going on? To demonstrate, so we ended up building a system that uses this type of cryptography to do resolution. So you have an organization, they're going to end up giving their data into some type of an encrypted bank. All right, so this is going to be where the data integration takes place. So you'll have a query that gets issued to this place, and then they're going to end up processing the encrypted data, they're going to merge everything, and then they give it back to some key holding site who ends up decrypting, and then you get to see if something matched or not. At this point, you don't see what the actual records were. It was just match, no match, and the computation's done over the encryption. So this is going to be really the most mathy section of this presentation. The way in which this was done, and which we tend to see this done in modern systems, is through strategies of work called homomorphic cryptography. And homomorphic cryptography says that you can take 2 messages and then you can compare their ciphertexts in this space and you won't disclose anything. If you're familiar with public key cryptography, RSA or PGP, or if you use encryption in Outlook, this is the same type of concept. So you'll have a public key that you can make available. You'll have a private key that you keep private. So you'll have an encryption function for what I'm about to show you. We use this function E. You'll have a decryption function. We'll just say that that's D. And then I'll just say that this is a message. We'll refer to that message as the ith message, MI. Okay. So there are 3 properties that are quite useful in this space. So the first one is that when you work with these, they're constant efficient. So if you multiply by a constant, it's actually done quickly. They're probabilistic. So that's why I was saying before, where you can take this name Smith, encrypt it once, and then encrypt it a second time. It will look different in both encryptions. And you can't predict what it's going to look like. And then the third one is that it's additively homomorphic in the system that we're using. And I'll show you what that means in a second. But additively just means that you can bring together 2 things that are encrypted. Okay, so this one I'll focus on a little bit more. So basically it says you take two encrypted messages, then you're going to have an algorithm that's going to allow you to combine the two of them. All right? So you can take the encrypted message 1, sort of add it to encrypted message 2. It requires a little bit more detail than that, but it will end up being the exact same thing as taking the encryption of those messages in their plain form, their plain text form. So what that means is that when you've combined them, when you decrypt it, it would be the exact same as if you've already done that merging. Okay? So what does that mean? What that means is that if you're interested in the name John, let's say, and that's M1, and you see John again is M2, in the bit space, you can just invert one of those. And so it would become M1 minus M2. If they're exactly the same, you'll end up seeing that it's a 0. If they're not the same, you'll end up seeing something that's completely random. Okay? So let me skip this a little bit. All right. Because I think I just explained how this works. It's not worth going through the crypto. Okay, so everybody understand how that works now? Of course. Right. I don't want to spend too much time on the details of the cryptography because really all I want you to get out of that is that there are cryptographic techniques that have been developed over the last 10 years that can be done to do these types of similarity comparisons or equivalence comparisons. Right. So the example, though, that I gave you with Northwestern in terms of testing their gold standard, this was done with data that was relatively recent, and it was all done out of the same institution. When you start looking across institutions, what you find is that there's a lot more typographical error, there's a lot more variation in the names, such that you can't just do this type of an equivalence test to check to see if things are the same. So people have been building things like data corruptors to try and simulate this, but because you want to have a gold standard data set in order to do an evaluation. So these types of corruptors have been built into record linkage toolkits that have been published, one being the freely extensible biomedical record linkage toolkit. We've put one out there. And they basically simulate what the Census Bureau has observed in terms of you see PH being replaced with like an F. You can simulate people's movements. You can change last names at the rate at which people end up getting married. But you can do this type of a simulation. Okay, so let's do a little bit of corruption in order to see how these types of record linkage strategies work. All right, so if you were to follow like the standard rates at which this corruption happens, so corruption, let's say, is on our x-axis here, and then we're looking at just a couple of performance measures in terms of accuracy of linkage, for instance, or the sensitivity of the system. So really all you take home from this is that you increase the corruption in the system, it becomes more difficult to resolve an individual. That's really all it shows. It makes sense, right? Okay, so it's social security numbers up in the blue, full names down in the red, and then that lower dashed one is just the combination of a couple variables. Okay, so in the example I was talking about in terms of this encrypted computation, there has been work in people who can do similarity comparisons in that encrypted space. So you can take an edit distance or a Levenshtein distance, and you can end up computing that without disclosing what any value corresponds to along the way. It turns out these methods were actually invented over a decade ago. We'll come back to that in 1 second, so just keep that in mind. There have been concerns that these types of strategies, the encrypted data, it's just, you have to take it with a bit of a grain of salt, because you have to say, okay, well, there's some magic going on behind the scenes. Do I trust the encryption? I'd rather actually work with real data, something that is I can touch and I can feel and I can feel comfortable that there's no weird outliers. So other groups have been suggesting that you take data and you do an in the clear transformation. You try and do a representation of it with something that makes sense. So a group, Monica Scanepio was up at Purdue with Elisa Bertino's group. One suggestion they came up with was what's called an embedding. So you'll take like a name and then you'll convert it, or you'll compare it to random strings. Okay, so let's say I give you a bunch of random strings out in this like weird dimensional space, right? There's a lot of different ways in which you can combine values to represent a string. And so you'll just measure the distance between my name and all those strings, right? And so now you'll say, well, I'm not going to tell you what the name was, right? But I am going to tell you what that similarity function looked like with respect to all of those anchor points within the system. And then I'll use that as the representation for this individual. And as long as we share what those anchor points were across all of the systems that are combining data, we should be able to get a consistent representation of this individual. And so this should be fault tolerant as well, because you can actually measure the distance between Brad and all of the possible strings. So that's one of the theories that people have suggested. Another one comes back to hash and bash, where instead of combining everything, you end up leaving it as its own little hash, and then you can check to see how many things actually matched up. This ends up leading to all sorts of problems, though, because you end up revealing frequency distributions with respect to each of these features. So that can be potentially problematic. More recently, our group and another group out in Germany has been looking at using Bloom filter strategies. If you're not familiar with Bloom's filters, basically what it means is you have a 0-1 representation and you're going to hash features into the 0-1 representation. So we've done n-grams with respect to these names, or just bigrams here. And so we'll take two hash functions, and we take this first portion of the name, we hash it in, we hit the first bit and the third bit, and then we do that for everybody. And we do that for both of these records. So now we've got this bit string representation of this full name. And then you can use something like a dice coefficient or a Jacquard coefficient, which is basically just set similarity. How many things did you have in common over how many bits that were set in total? All right, so here you can see that in this situation, JOHN and JON had about a 77% match rate at this point. Okay, so to really hammer home why these types of transformations in the clear may actually be desirable in their own right, this was a comparative analysis with 100,000 North Carolina voter registration records. If you're not familiar with this, North Carolina has become a really cool proofing ground for record linkage, because you have this publicly accessible free voter registration database that is updated over time. And so we can watch where you're all moving to, because that's public record. And a friend of mine out in Australia has actually been downloading that database every other month for the last 5 years and has been building movement patterns off of it. Creeped out yet? All right, so what exactly did I just throw up? This is like random graph toss, right? What you see here on this x-axis is this is the hit rate. This is the true positive rate in terms of if I do 100,000 records that have been left in their original form and corrupted to a certain extent, how well can I match them? Okay, I'm not going to go through how much corruption we did, but it wasn't that much. All right, so the runtime over here on the left, really just pay attention to the order of magnitude. We're using commodity servers here. So you're looking at something with like a couple gigahertz of capability and probably about 30 gigs of RAM in terms of doing this. All right, so this thing up at the top, it has really, really super high accuracy, and it has runtimes that are ungodly slow. That's the crypto approach. That's homomorphic cryptography. This is where it was about 4 years ago. It's come down by about an order of magnitude in the last 4 years. This is still multiple orders of magnitude away from being anywhere in the pragmatic computation space. These guys, these are all your transformations in the clear for the most part, and there's a lot of different variations on them, Bloom filters being one of them. At the same time, we were looking at the security versus the accuracy. We looked at the security in terms of the mutual information between the encrypted data or the transformed data and the original data. In other words, how predictable was the output from the input, right? And so what you end up seeing is that these things which have high true positive rates, you end up wanting the ones that are over here on the left. You want them to have low mutual information, So what we end up finding is that the Bloom filter technique that we were just suggesting could end up being a good way to go. It ends up having low mutual information, it's not predictable, it seems to have pretty high accuracy, and it runs quickly. And that's how we got to this point. So if what I've just shown you is that error tolerance is possible if you do this in a very careful way, so then the question is, why don't people do it? Right? We keep asking this question of like, what we see in the literature is that people just do hash and bash, and they hash and bash. And there's a lot of things that people publish and that they argue why this can't be done. And so I kind of took these as almost like hypotheses that I needed to disprove. Okay? So here was hypothesis or problem one, which is that there's protocol design complexity. We see this all the time. In fact, in a pretty major informatics journal, they explicitly called out our own methods, and they said that they're not computer scientists and they can't figure this out. And that was quite disturbing to me. So now, to understand, you do have to recognize that there are cracks in the system. And so the criticism about this type of a methodology, a transformation in the clear methodology, is we're partially at fault for this. And the reason was that, so I mentioned that there was a competing group to us that was coming out with this idea. They beat us by a couple months. We took a look at what they did, and we found that it was, this is on the web, so if somebody's watching and you're from this group out in Germany, I'm really sorry, but it was insecure. Okay, I've said it. So the problem was that an individual who receives this type of in the clear transformation, this 0-1 representation as an example, they may have some knowledge of where those things came from. So for instance, if it's built on names, we tend to know what names look like in the population, and we have a general idea of their distribution. And as a result, the recipient of that data, they can build constraint satisfaction programs that can crack that system, just like you would crack traditional hashing functions. So I won't go through the details of how we did it, but basically imagine well, actually I will go through it. But the simplest approach to this will be that, so this is the overall system, it's a process. So basically you can get constraints based on what you see in the properties of these functions. Okay, so remember I gave you an n-gram encoding function, like bigrams, JO, OH, HN, right? All right, so I've got this encoding function. Now I can model three aspects of this. I can have variables, domains, and constraints associated with it. Okay, and then I'm also going to have the constraint satisfaction program state. And this is going to be the set of assignments that are possible between my variables and the underlying values in that domain, given the constraints that I've now observed. All right, so we're going to create a simulator for this encoding function on each of the n-grams. And we'll call this a belief function. All right, so now initially, each thing is equally possible. Okay, we'll just flip this to a 1. That's all we say. Everything's equally possible. So initially, everything is available. Everything can be assigned. And then we'll have an assignment. So let's see, for instance, that the name Joe ends up at 1001, 0001. All right, and so here's the transformation of this name. Yeah, sorry. There we go. Yeah, so JO has flipped a couple of bits. I don't know what OH has been flipped into. I don't know what HN has been flipped into, but I've also seen, let's say, OE has been flipped at this point. All right, so I've got some constraints that I've now introduced in the system. All right, and now when I flip John into the system, I end up seeing some further constraints. Okay? All right, so now that's one of the ways in which we can represent what's going on and try and simulate and crack it. Another way is that we can introduce several additional constraints. So, for instance, all of our encoding should be obtainable with our current belief. Again, we'll skip this part. And then there is a minimum location constraint in that there have to be a certain number of bits that do get set. Right? This is true. So there's an expectation that in this Bloom filter, we're going to have a minimum portions or positions that get set. Okay. All right, we'll skip that. Okay, so what I've just shown you, without going through all the details, is that you can set up these types of CSPs. So without going through the formal details of how this happens, let's look at how it plays out. So imagine I took the North Carolina voter registration list, and then I'm going to pull out a sample out of this. All right, so I've got 20,000 records. 3,500 of them are distinct in terms of the features that we're using. And then we're just going to do 10,000 data sets of 20,000 records each. Okay, so we're going to keep pulling. So we've got 400 names selected as variables from these candidates. All right, now in the Bloom filter parameters that we chose, we simulated exactly what had been published in the literature, take 15 hash functions, 500 bits, and split things into bigrams. All right, so what you see here is a demonstration of just how well we cracked the system. So how many things did we end up cracking or try to crack, and then what was the compromise success? So this was basically the precision up there on the top, and that's the recall on there on the bottom. So we end up cracking about 10% of the names at that point. And we end up, for every claim that we make, we basically get to the point where we're at almost 100% correctness in our cracks. So that was a concern to us. Okay, now what I showed you though was a very theoretical situation, and this was quite intriguing because it assumes that data is clean, and in the real world it's not necessarily clean. So we went back to look at a more realistic situation because we didn't have any other resource from North Carolina to try and compare the voter registration list against. So we went back to Tennessee and we attacked Vanderbilt just because we could. So we took the Davidson County voter registration list, which is where Vanderbilt's located. Didn't cost us anything. Had about 283,000 records with a zip code that was in Davidson County in it. We then looked at Vanderbilt patient records for individuals who had geographics that would be within this county. So that was around 240,000 people. And then we looked at the 100 most frequent street names, and then we looked at the 37 most frequent 5-digit zip codes to try and see if we would be able to crack these. So basically, these are the variables with respect to the zip codes, just as an example. The frequency bounds that we end up building, the top is the highest expected frequency if you do a Monte Carlo sampling. And then same thing as the triangles are the lowest possible frequency you would expect, and the greens is what we actually observe in the data. And so you can see that for most of them, we get the correct bound. For some of them, we are slightly off on the bound. That's a problem. Because if you try and actually run a constraint satisfaction program where some of your variables are incorrectly specified, they don't cover the space, it will not terminate. It will not actually get to the correct answer. So what we did was we systematically expanded our bounds until we found a point where we could actually execute it, and the thing exploded on this. So these little white lines are where the system was before. It's basically the size that you look at here, the size between the upper and the lower. And then the black is what happened when we did the systematic expansion, became the complexity in the system more than doubled. Now, what was interesting about it, though, was that we were able to crack 95% of the zip codes once we did that. So complexity went up, but it was still crackable. But this becomes a really interesting economic question because it took us almost a day in order to do this crack. It required us to find the right relaxation parameters once we could run the attack. And each of these relaxations required almost 2 days for us to terminate where it said I couldn't get a solution. Right? So this thing, I think all in all, it took a long time. Okay. Names, on the other hand, this was an extremely challenging problem. So not all names were represented, we found. So we focused on the top 42 names. No solution was found after about a week of computation. So we went up to the top 20 names. And then what we found was that there was a solution. We got to it in several seconds. we made 20 claims, 4 out of them were correct. Not so great, right? So this basically said, so what's going on? So why were we able to crack the system? We were able to crack the system because we were able to treat each of these fields independently. And that was the way the original systems were designed. You build a Bloom filter for every feature. And we said, so what happens if we just mix it all together, right? This is no different than actually creating a composite hash function. So then once we mix it, we shuffle it, so I don't tell you where any of the bits came from, and maybe this will work. So we come back to North Carolina, just as an example. We run these composite filters over all these fields that I was talking about. Again, we take 20,000 from the North Carolina voter registration record. We look at various combinations, even as simple as 2 fields. What we found was that nothing was crackable in any way, actually. The distribution of the combination of first and last name, for instance, became almost uniform. Same thing happened when you started putting in like city, zip, and name. We ended up looking at a couple other features. So this one was when we made the system a bit larger to see if we could get some of those names that were a bit more common to really start to jump out in the frequency distribution. We were able to crack one name with a combination of first name and last names. By the time you started adding one additional feature, nothing was crackable. So you might just be going, duh, right? You combine a couple of features, of course it's going to be a lot more secure. But what we've just done is we've combined a bunch of features, and we've still left the potential for direct similarity comparisons, which was where we got excited. Okay, so the implications for this is that you can crack these types of transformations in the field, in the clear, if you don't parameterize it in a clean manner. But in practice, it's going to be hard to do so. So, who are you really worried about is the question, right? If you put these things out on the web, you may have to worry about it. If you're worried about some centralizing authority, let's say RTI ends up managing the process for all of the hospitals in North Carolina, they're a more trusted entity, you may actually not have a concern at that point. And so then you have this question of, so composite filters can stop the attack, as I was alluding to. It will lead to a little bit of a loss of accuracy. How much? Okay. So we took it a couple steps further. So for instance, this attack, it may still work that we were suggesting. The attack may still be able to separate where certain fields, which fields contributed to which particular bit. All right, and that's just because they have the certain probability, a different probability of setting a bit. For example, so here's surname, forename, city, street address, ethnicity, and gender. This is the average rate at which a bit actually gets flipped. And what jumps out at you really quickly here is that ethnicity and gender clearly gets set at a much lower rate. All right, so we were concerned that somebody might be able to separate the system and then rerun the attack. So this led to the next innovation in this strategy, which was just dynamically sizing the Bloom filters. So if you dynamically size them, you could ensure that you can have an equal likelihood at which bits get set from each of these fields. So just as an example, this is how you would dynamically size them. So when we did dynamic sizing, to prevent that, we ended up leading to a complete uniform distribution, which prevented that type of an attack. So we basically in many respects, we're building a hardened hash function at this point. So at that point, the frequency, as I just suggested, it doesn't reveal anything about these fields, so we felt good about this. And then we introduced a minimum security threshold. So we wanted this parameterized. So we said we want to ensure that every bit maps to a minimum number of fields, right? So here's a distribution of how many fields each of these bits are going to correspond to given the frequency with which it will be set. And so the ones that we would be interested in are those ones that end up in the sweet spot that end up being higher. And that's the bits that we will end up retaining to represent the individual in this filter. Okay, so dynamic sizing, how did we get there? Basically, the way that we do this is we run an expectation maximization model to check to see which of these fields are the most discriminatory and the most capable of being retained and being in the uniform distribution. So we're going to end up sizing this proportionally to their discriminatory capability. Again, we end up with our big filter at the end of the day. Okay, so I basically just gave you a big trust me on the expectation maximization framework. If you want to know more about it, we can go through it, but trust me. Okay, so we then we got to this point where we're saying, so we want to make this quick, right? And the whole point is we want to be able to say, this is person A, we want to find their counterpart, let's say A prime. So here's an example of what we're trying to do. This is what we call the neighborhood test. You've got two data sets. Let's say you've got Vanderbilt on the left, and you've got, I don't know, Duke on the right. So Vanderbilt's in that black line, Duke has got patients that are not in the black line. And what we're going to ask is, for an individual, how close are you to your nearest neighbor, to your person of interest? So you take somebody from one of these record sets and you say, who's nearest to you? All right, and what's the point at which I get to the correct record? That's how we're going to measure the accuracy in the system. All right, so at this point it took 3 steps. Okay, so we took 1,000 records from North Carolina, just as an example. We did 10 replications of this. We checked to see if we could find the partner. And this was how often we were able to find the partner given the security constraint. So even by the time we say a bit can map to no less than 5 fields, we got to the point where it was about 97% accurate in finding the partner. If we wanted to reduce that a little bit in insecurity, we could get it to about 98% accurate. We didn't find that that trade-off was necessary at that point. So we felt pretty good about the way these Bloom filters would work. Now, here's where things get fast. And the whole point of this talk was that it was called scalable approaches, right? In order to make it scalable, you have to be able to do lots of comparisons relatively quickly. In the space of record linkage, you have to imagine you have a data set of like 1 million people. You want to compare it to another data set of 1 million people. 1 million by 1 million is a lot of computation to run. You don't want to run it all. So what the Census Bureau, what other places tend to do is they say, we're going to pick a field that we think is relatively consistent, and it's going to segment you pretty easily. So we'll take like the first letter of your last name. We'll say everybody with an S, we compare them. Everybody with a T, we compare them. So in doing that, you have this nice semantic that you can use for segmenting the system. This is what's called blocking. So anything that doesn't end up in, let's say, one of these white blocks, it wouldn't be compared. All right? That speeds the system up tremendously when you're doing those things in practice. The bit strings that we've just introduced it's not as clear how you do that. So we ended up turning this into a partitioning problem. So this was the example I gave you before. Just as an example, you basically have bins. They're basically hardly partitioned bins. So none of the S's end up in the bin with the B's. This actually kind of worried us about the way record linkage worked, because that's not the way that the world actually does work. It doesn't have these types of hard partitions. It implies that there's no typographical error that happens at the beginning of a name or the beginning of an address, for instance. So we ended up adopting a more soft partitioning strategy. The theory behind this is what's called canopy clustering, where you'll end up picking a record and then you'll say, take a radius around that record. And then everything that's within that radius is covered. And now go pick up another record that has yet to be covered and then build another radius around that one. They may overlap, which is why you end up with one of these canopies. But you'll end up with this type of a soft or fuzzy clustering that should give you better fidelity at the end of the day. So in order to do this, the big data community has been working on what are called locality-sensitive hashing functions for indexing the web really quickly. Locality-sensitive hashing functions basically just say that you sample bits from this bit string with replacement at a certain way. There's a couple of different strategies for doing it. One's a Hamming function, one's a Jacquard-based function. But in doing so, you basically are doing a downsampling of the system. You go from 5,000 or 1,000 bits, and now you go down to like 10, right? And because we're trying to do a compression. So we did this. We apply a locality-sensitive hashing function. The one that ended up working the best for us was what you would call the Hamming distance one, which is one on the left, Jacquard second, canopy clustering in general is third, and then what the Census Bureau does is the last one. And so this is, you can see it reduces, it compresses down to about 1% of where the size should be, 2%. All right, so we have heavily reduced the system, and so then this says. So that's, you reduce the size. Did the records that you were interested in, are they still in the same group? Did they go to the right cluster? And so with the Hamming distance function, we found out that more than 99% of the records we were interested in were still there. So we had this huge compression, and we ended up having almost no loss in fidelity. We got excited. I don't know. These things get me excited, right? So I'm a computer scientist. Okay, so now you've got to bring it all together. Because the whole point about record linkage is you have to do cradle to grave. You've got to transform the data, you've got to block the data, you've got to do comparisons on it, and then as soon as I say that to an IT specialist in any hospital, by the first words that come out of mouth, they go, is there software that does this? And so we say, okay, well, yeah, but we're getting there. So you have to bring it all together, though. If you study each of these things independently, as I've been pointing them out to you, it doesn't really create a solution. It's more of an academic investigation. So we built this system, and we said, so how does all this work in combination? That's where we brought in our software. To get to our software, we had to do a big evaluation of what everybody was doing with record linkage in the country. So we looked at a bunch of features. We looked at the tools that were available, whether or not it did private record linkage, if it was free, because everybody wanted it to be free, nobody wanted to pay, if it was open source, if it was extensible, and if it supported communication between multiple sites. Because what we found with a lot of record linkage software is that you can run it at one site and it has no relationship to another site. So basically what happens is that everybody just encrypts like one big file, they send it off to some third party, they decrypt it, and then they do the analysis. We wanted to have it interactive. And did it have a front-end graphical user interface? So you may be familiar, if you work in this field, you may have seen some of these tools. Some of them are like the Link Plus. The only thing that's really beneficial here is that it's free. Febrile ends up getting us to this point where it's free, it's open source, it's extensible, it doesn't do privacy, it doesn't have the communication capability. And then there's other tools that are out there, they're getting a little better. And then we get to this point where eventually we got to OpenEMPI and OpenMRS. OpenMRS, this is what a lot of developing countries use within their electronic medical record systems. OpenEMPI, this is the Open Enterprise Master Patient Indexing toolkit. It was built for California's Health Information Exchange, covered all the features we were interested in. The only thing it didn't do was privacy. So we built a system that extended that thing into privacy, and we called it the secure version. This is like the prettier version of my line is better than your line, only green and red. So okay, so that was problem 2. So how do we build the software? Or what do we do to build the software? So problem 3 that we keep hearing is that it has to cover the life cycle, as I was alluding to. Because these privacy-preserving algorithms, they are not necessarily short. You basically have a function that goes like this, or a process that goes like this. You have Alice and Bob who want to compare their records. They need to get salts for their hash functions. Then they have to do all of this stuff. Okay, that's what we ended up publishing in a paper. That's the process. And that was where we got criticized for being too complex. So we said, well, we'll just put that into the software, and you don't ever have to see it. So that's what we did with SOE MPI. If you want to download the software, it's publicly accessible. We already have some companies who are building technologies around it. It supports 3 different roles: data providers, the integrator, as well as a parameter manager who figures out how to weight your bits. There's some details there. And it gives you the ability to do key generation and tuning of the Bloom filter parameters, data transfer between all the roles, and it facilitates that entire life cycle of the linkage process. I will run out of time, so I'll skip how the software is architected. But what I did want to show you, without going through the screenshots. Okay, so we did an evaluation. Once again, we picked on North Carolina. All right. So we now take 10 data sets, 10,000 records, and we're going to subject it to that whole corruption process I gave you a slide on before. Nothing new there. All right, so we'll do some corruption. And so now we've got 3 parties. Alice and Bob are comparing records, Dan, who's doing the integration, and then we have our strings translated through a phoneme model. We're going to do some blocking on what's called a sorted neighborhood algorithm. That's the standard that record linkage communities use. And then a matching function that's also considered the standard. This is what's in the non-secure toolbox already. So that's baseline. Then you've got us. We've introduced a couple new parties. We're doing some hashing. We're doing the locality-sensitive hashing, and we're going to do a set similarity comparison. So we're introducing a lot of overhead here. And we wanted to know, how fast can we actually make this go? So baseline's on the right. We're the one in the middle. This is the number of seconds it takes to do anything. So to ingest those data sets, it's a second difference. In order to get all of your salts and do a lot of the sending of these encoded data sets in order for generation of those salts, it's about 7 more seconds. In order to send the data to whoever's doing the integration, it increased by about a factor of 4, but you basically are looking at 6 seconds versus 20 seconds. Okay? And the reason why this happens is that we've basically blown up the size of the data set a bit. And so blocking, 47 seconds versus 58 seconds. And so overall time, we basically took it from 1 minute from doing this process to about 1.5 minutes, which we felt was pretty good. We felt that that was still in a real-time type of analysis environment. All right, so I get to the end. I've swept a lot of things under the rug because there's a lot of research here. Where do we get to? Private record linkage, if you do it in the clear, the fastest way we could possibly do this while accounting for typographical error, we find it's slower than what people currently use in the market for record linkage, but not much. You can still, on a moderately sized data set, do this in less than 2 minutes. The majority of the time is all in the encoding process. What's nice about that is that that can be parallelized easily. The linkage process is a little bit slower, about 1.2 times slower, not much. We do find that the speed will vary with the data set. It varies linearly in the number of records because really all you're talking about is just its hash, right? So you add more records, it's going to take a little bit more time. And it's quadratically in the number of bits that are selected for blocking and record comparison because these are similarity functions, right? So I'm basically saying I got to see how many things are in common, how many things are not in common, so I have to compare that all. So what are these next steps? What are these opportunities? The system we built, it's out there. The open source version is only single-threaded. We've had some groups that are starting to look at modern Hadoop or MapReduce environments that people use for big data management, but that would be useful. There are some concerns that the system doesn't have any cryptographic primitives, so you can't simulate secure multi-party computation. Now, I made the claim that it's slow. You probably don't ever want to do this, but it's getting faster every day. IBM's putting technology out there that there are toolkits that can make it faster. So there are toolkits like one of our collaborators at the University of Texas at Dallas put out a Pi-A toolkit, which does secure multi-party computation of the form that I talked about. That needs to be integrated. And moreover, if you're a software geek, then there's all sorts of questions about how to make the software pretty and stateful and manageable. If you want to know more details, you can read it. But really, we want to have something that is enterprise capable. We want to have something that is not going to be sufficiently clunky, but we put proof of concept out there and a working piece of software for anybody who wants to play around with it and make it better. The other limitation is that it's only on a Postgres database. So if you want to connect to SQL Server or you want to connect onto Oracle, we currently aren't supporting that, but we are supporting JDBC connectivity to the database, so you can call those ODBC resources as necessary. The biggest challenge is actually some of the security associated with JBoss, if you're familiar with it. We run all of this on JBoss. It's all on a Java server. There is no secured line, so things are getting sent in the clear across the network. We did that partially for speed and efficiency issues more than anything else, but you could claim it's not the most secure system. All right, so this is probably one of the most technical talks I've ever given on this topic. So I'm gonna again come back to the acknowledgments. There's been a lot of people involved in this, a lot of software engineers, a lot of developers, and so if you have questions or comments, I'll stop. I started a couple minutes early, or a couple minutes late, so I still stopped on time. So if you want to drill down on anything, I'm more than happy to afterwards. Or if you want to know anything that's general about it, let me know. Otherwise, I'll stop.